So the first thing that we will discuss about optimization is what do we mean by optimization? Optimization is the process of creating something which is as effective as possible. That's the general meaning of the word. Typically, we have some kind of a function, and we are looking for the point or the points that have the maximum possible value of the function. So we are trying to vary the independent parameters and then calculate the value of the function until we find the location where the function is going to have either maximum value or minimum value. Both of these are considered optimal points, depending on what's your objective. So if the function represents some kind of an undesired phenomena, then you are looking for the minimum value. If the function represents a desired phenomena, then you are looking for the maximum value. By the way, solving the maximum and the minimum are exactly equivalent. So any function that you want to maximize, you can figure out the location of its maxima by inverting the function, the sign of the function, or flipping the function. So if f of x is equal to x, and you want to maximize that, this is equivalent to minimizing 1 over x or minimizing minus x, right? It's exactly the same as maximizing x, right? So solving for the minimum or the maximum is exactly equivalent. All you need to do is to go and flip the function itself, either by taking the inverse or the additive inverse, so the multiplicative inverse or the additive inverse. Of course, the multiplicative inverse is a little bit dangerous because if the function passes through 0, the inverse is going to give you something that you cannot deal with, right? So you have to be careful not to use the multiplicative inverse all the time. Most of the time, it's much easier to use the additive by flipping the sign. So maximize f of x is equivalent to minimize minus f of x, right? Okay, that's the easiest way. Why am I saying this? Because most of the commands in MATLAB that you will find are always trying to minimize a function, right? So the function is called fmin, fmin.com, fmin search, and so on, right? So it's always minimizing. Now you might stumble and say, but I want to maximize. It's very easy, just flip your function, switch the sign of your function, okay? Okay, so that's the idea of optimization. So we're trying to locate a place where you get the maximum value. Keep in mind that most of the time we are not really dealing with the simple high school situation, which is like a single variable and a function of a single variable. And most of the time you are dealing with a function of multivariables. Whether even if you are dealing with something in space that's at least 3 variables, in many cases you are dealing with more than 3 dimensions, okay? Depends on what are the parameters that you are looking at. So if your objective needs to be optimized in terms of temperature, pressure, location, time, and all of these, so it becomes, if these are all the parameters that you can vary, this is the dimensionality of your problem, okay? So in that case, in case of dealing with multi-dimensional situations, the representation graphically is not simply a function in 2D as we see here. There are other ways to represent multi-dimensional functions. One of those is something called the contour plot. So the idea here for the contour plot, for example, if you have a function which is varying with respect to x and y, then each one of those closed loops or closed lines represents a fixed value for the function. And then the next one is another. As you go through this line, the function f has the exact same value for different x and y, right? That's called the contour plot. You can also do mesh plot for 3D graphs and so on. So just keep in mind that most of the time we are dealing with the non-simple case where you have actually more than one variable. Okay, so it's not a single variable situation. Now, one other important thing is when you are trying to optimize something, typically you are looking for the global optima, the best value that you can achieve, right? whether it's the optima as maximize or the optima as minimize. However, in many cases, your function will have lots of hills and valleys, right? So it will have a lot of points where in a certain region, it reaches a maxima, then it goes down, it goes somewhere, maybe it reaches some minima, goes up. Now the global is if you are looking for the maximum, is the highest among all those. That's the global maxima. And the global minima is the highest among all the minimas that you will encounter, okay? Those functions that have multiple maxima and minima, they are called multimodal functions, or generally speaking in the literature, they call them non-convex functions, because a convex function or a concave would have only one optima or one value or one hill, right? It will not have multiple peaks, okay? That's called a convex, which has only one of those. In all the other functions that does not have a single one, it has more than those. It's called multimodal, or it's called non-convex function, okay? The problem with non-convex function, remember when you learned optimization in classical mathematics, or the classical way to do optimization, you were looking for those locations, and you identified them by taking the derivative of your function and equating that derivative to 0. Why? Because at those peaks, right, the slope of the line is horizontal, which means that it will have a slope equal to 0. So that's why you took the derivative to get the slope of the line everywhere, and then you equated that to 0 to figure out the location. Now, if you have too many of those, then that equation will have multiple solutions, right? And you have to go and examine each one of those, evaluate the function at each one of those, until you figure out across the whole range which one has the highest or the lowest, depending on whether you are looking for a maximum or a minimum, right? In many cases, this is a very expensive process. You have really a lot of those, and to search across them one by one, especially when you deal with multi-dimensional systems, it becomes really a very heavy task. But that's basically the only guaranteed way, okay? Now, if this is not the case, if you are dealing with a convex function, then it's easier. It's easier from the perspective that you will have only one solution, but sometimes that solution, you cannot get it mathematically. You cannot solve the equation, because the equation, for example, is a set at the location of the maxima or the minima. You have a set of coupled equations. So you cannot really solve them by substitution, or maybe a set of nonlinear equations, right? Solving them together is not going to be easy, and this is where you actually start looking for numerical approaches to find the maximum point or the minimum point. That's called numerical optimization, right? Also, in other cases, when you are dealing with multimodal functions, again, even if you can solve that equation, the number of solutions is going to be large, the number of possible solutions, and searching across them is going to be very expensive computationally and time-wise. So we need other approaches, typically also numerical approaches, so that we can overcome this problem, okay? So let's look at those approaches that are used for numerical optimization. The first one, and the simplest one, and it works actually for single-dimensional equations, so basically, or functions, sorry. So basically, you have a function of one variable only, right? So something like the example that we saw earlier, right? So you have only a function of, this is x, the independent variable, and this is f of x. That's a single-dimensional, a line only, and it's a function of one variable. And in this case, if the function that you are dealing with is a convex function, okay? However, it might be complicated in terms of expression, and then it's either very difficult for you to figure out the derivative of the function, or if you figure out the derivative, it gives you an equation which is not easy to solve, right? A nonlinear equation, for example, with complicated terms, cosine and x square and logarithm and all of these together, then solving that equation is not going to be easy. The approach to find the peak point or the optimal point is called, one of the approaches is called the golden section search, okay? And the way the golden, we call it the golden section search because it uses this ratio, 1.6180. This is called the golden ratio, and the reason for calling this a golden ratio comes from solving a particular second order equation. I think this term has 1 minus the root of 5 divided by something. So, and it has specific characteristics in arithmetics. Okay, so they call that the golden ratio. Okay. Now, using that ratio, the approach works as follows. Okay, so you start by, let's say, in all optimization problems, you are again practically you are trying to solve within a certain range of the independent variable, right? You are not really trying to solve up to infinity. Okay? So you have a certain range. I know that, for example, the height of my building cannot be less than 3 meters, and maybe in the area that I'm doing this building, I cannot really exceed 30 meters, right? Because of some restrictions. So I'm searching for the optimal height from a particular perspective between 3 meters and 30 meters, right? So I have a certain range for the height, which is my independent variable, for example, in this case, okay? So you have a certain range. The range is identified by the lower bound of the independent variable, XL, and the upper bound, XU. And you are trying to figure out the location where you have the minimum between those two ranges, okay? Now, the way you do this is you go away from XL, a distance D, right? And that distance D is dependent on that golden ratio. So D is equal to the golden ratio minus 1 multiplied by the upper minus the lower, as you see the equation up there, okay? This one, okay? So this defines where is the location of X1, okay? It's a XL and then added to it D, that's X1. And then X2 is the upper limit subtracted from it D, and that's called point X2. Okay, so you have X1 here and X2 here. Okay? Those are two just selected points based on these equations. Okay? Based on the golden ratio equation. Okay. Now you check if the function value at X1, so the function value, this value, is less than the function value at X2. Where is X2? Here is X2, which is the case in our situation here. So if this condition is true, then X2 becomes the new lower bound. So you ignore this guy, no longer need this, right? And then this becomes your lower bound. So now you start from X2 and you go all the way up to XU, upper value, XU, okay? And then X1 becomes the new X2. Remember that, okay, it's shown in the figure right underneath it, right? Pointer, okay? So this became your upper point, lower bound, because this condition was true, So this became your lower bound. You no longer care about this range at all, right? And then this point, X1, becomes your X2, right? Remember that we have X1 and X2, right? And then you calculate a new X1 from this equation, right? But remember that the D now is gonna be calculated based on the range from X lower to X upper, the new range between X lower and X upper, okay? So your D now becomes smaller. As you did this move, your D becomes smaller, which means that now you are searching in a smaller range, right? And then you repeat the same operation again. Now you have XL, X upper, X2, X1. You go for the function value at X1, the function value at X2. You compare them. If they satisfy this condition, you repeat the same operation. What if the condition was the other way around? What if we ended up with those values, X1 and X2, such that the function value at X2 was actually less than the function value at X1, which is not shown in this figure, because in this figure, the function value here is higher at X2. But what if it was the opposite, okay? This means that we are on the other side of the minima, right? So this means that we are on this side, rather than being on this side as we were in the previous case, right? In that case, the replacement is going to be that x1 becomes the new upper limit rather than the lower limit. Remember here, we took x2 and we made it the lower limit. Now, if this condition is true, you take x1 and you make it the upper limit, and your search becomes in this range between this new upper limit and this existing lower limit, right? And then again, x2 becomes your new x1, and then you calculate a new x2, and then you repeat the operation and so on, okay? Keeping doing this operation, and you always check when you reach a point where x1 and x2 are very close to each other, that's where you stop. That means that you have converged to the minimum point or the optimal point of that function, okay? Any questions about how does this work? Can anyone write the code for this in MATLAB? By the way, you have now very nice MATLAB license access, right? You have tried it already? University bought a campus-wide MATLAB. You can access that using your student ID.
So we're using the cloud Citrix one.
No, Cloud Citrix, no. Use direct, go to MATLAB, go to matlab.mathworks.com, do it now. From your browser, and they prefer that you use Google Chrome browser. Yeah.
Is it one for MathWork, and I have to use my Blackboard ID for it?
You have to use your email.
QU email. Yes, I did that.
Yeah.
Take a latest version.
Yes, you work with the latest version. All the packages are there, except very few. Like 90% of the packages are functional, and the computational quality is very nice. So they use the server for the computation, and it's really nice. So try that, it works really very nice. You don't even need to install MATLAB in your computer. And it works from outside the campus as it works inside the campus. If you just access it using your email address, you need to create a user, so just for everyone, so you know what you need to do. You need to create a user, you go to MATLAB, and then you say, if you did not do that before, say create new user using your email, right? And then once it will ask you to put some password, it's not the university password. Once you put that password, it will identify that this is a QU email, and automatically the license will be available for you. You will have access, and then you say, open MATLAB online. It's a button that you click on the website after creating that user and logging in. Open MATLAB online, it will give you the full interface of MATLAB inside your browser. Then you can do whatever. And you also have a cloud space where you can save the files there. And if you like terminate the session at some point, it keeps it as it is. Next time when you log in, you find it where you left it off. Okay, so that's very nice. Try to use that. It works off campus, on campus, all the packages, all Simulink packages, everything is available. Okay. Anyways.
Can we extract the files like you said it will be saved in the server?
You can also save it locally if you want, no problem. Yeah, you can save it either on the server. I think you have something like 30 gig or something like that of cloud space on MATLAB itself. And you can also, if you want, you can download the files locally. Yeah. Okay. But whenever you want to run them, you have to upload them to, if you want to run them through the online. The other option is install MATLAB, like go there, log in, download MATLAB, install whatever you want. You don't need to install all of it. And then once you finish the installation, it will ask you for username and password. Use the ones that you used for your account. It will automatically work with all licenses available for you. Okay, so, and it works off campus as on campus. So no Citrix, no slow stuff, nothing like that. Okay. Okay. Anyways, next. So this is just. I left an example here in the slides, which is the function gold minimum, or the gold search function for finding the minimum, and it's written for you. You can look at it, try to retype it again, understand how it works. Not now, offline, and play with it, see if you change the variables and so on. As usual, those guys are just. Always keep this in mind. If number of arguments is less than this, greater than that, these are just sanity check to make sure that you pass the minimum number of required parameters to the function when you call it. So these have nothing to do with the logic of the function itself. The actual logic of the function starts from here, going all the way until the end. Okay, so the rest is kind of programming. What do you call it? Doing better programming. So if someone calls the function with wrong number of parameters, they get an error instead of the system crashing or MATLAB stopping or whatever. Okay, that's the only reason for having those ones. Okay, another approach to solve one or single dimensional optimization problems is called the parabolic interpolation. So parabolic interpolation is, as the name suggests, you have a function that looks like whatever. Okay, so this is your actual function, the black line. Okay, so you have a function that has a certain peak, whether it's a max or a min at some point, right? And then you want to figure out the location of that max or min. One option to do this is to go and pick a few points from that function, and then you fit to those points a parabolic. Parabolic is a second order equation, right? The one that can either be convex or concave, right? So you fit it to those points that you selected. Typically, you try to select points such that, of course, you don't know the shape of the function ahead of time, right? But typically, you try to select those points such that they have one larger and two smaller, or three different points with three different values. You don't pick points that are very close to each other. You try to spread them around so that they can cover, hopefully, they can cover the range where the maxima or the minima that you are looking for exists, okay? And then you fit this to it. The equation here is the curve fitting for that. Again, it says here you pick, so the approach works as follows. You pick 3 points from the actual function, right? x1, x2, x3, and then you fit to those 3 points parabolic equation, and then from that fitting you get a fourth value. If you substitute the values of x1, x2 and the function at x1, x2 in all of them, then you should be able to get a fourth location. Then you take that fourth location and the two surrounding it. So if that fourth location is greater than x1, less than x2, then you use x1, x4, and x2. If you find that it is between x2 and x3, then you use x2, x4, and x3 as the new 3 points. Do the same again, and then you get x5. Look, where is x5? Use it with the two surrounding points. The result is you keep on fitting closer and closer until you fit the parabolic very close to the location of the maxima or the minima. And then at some point, when x, the new x that you get, is very close to the last one that you got, you stop the search at that point, okay? Because this means that doing more iterations is not gonna get you any better results, which means that most probably you are already there at the point of the maxima or the minima that you are looking for, okay? Now these are some MATLAB functions that uses either the golden section or the golden search, as well as the parabolic fit, and some of them actually they try a hybrid technique. So they use this and then they alternate to use the other and then come back to the search and so on, so that it can converge faster. All what we have looked at was actually for single dimensional, right? So 1D equations, and not only that, they were also 1D functions with a single maxima or a single minimum, okay? And now let's look at when we deal with, this is just that when you deal with multi-dimensionals plotting, you can use some other tools from MATLAB. Let's see if we actually want to deal with multi-dimensional multi-dimensional situations. But before going to the multi-dimensional, there is also one function in MATLAB. It's called fmin search, okay? And that fmin search is capable of trying as fast as possible to get you the global minima or maxima in a function which is not convex. So a function that has many maximum and minimum, right? In that case, it will try to figure out all the locations of the maxima and the minima within the range, and then compare all of them or sort them until it gets you the highest value, okay? That's called fmin search, okay? just an example of using the function, so I'm gonna skip this. Now, what if you want to deal with a multi-dimensional situation? There are, again, a number of algorithms that can be used to do numeric optimization, so figure out the optimal point of a particular function, which is a function of multivariables. Okay? One of those is called the Nelder-Mead method. And the method is a bit interesting to follow it up. Now imagine that this figure that you see on the right side, this figure that you see here, imagine that this figure is now it's shown only in two-dimensional. Typically, you will have, for every set of two variables, you will have a similar figure, okay? I will explain this a little bit later. But for now, let's look at if I have a function, right, which is currently, let's say the function f is currently a function of x1, x2, x3, x4, okay? Start by looking at f as a function of x1. And I want to figure out the location of the maxima or the minima. So that's a 2D situation, not a 3D or anything. So we are still dealing with two-dimensional situation. Now in that case, you start by picking 3 points, A, B, and C, random points on the space, okay? And those 3 points, you label them A, B, and C under this condition. The one that you pick as A is the one that has the lowest value of the function. The one that you pick as point B is the one that has the value higher than the value at A, but smaller than the value at C. And the one that you pick as point C, the one that you label as point C, among those 3 points that you picked randomly at the start, is the one that has the worst performance. Now, why we are calling this worst performance? Because our objective here is to minimize, okay? So this has the best performance in terms of the value of the function. This has something in between, and this has the worst performance. The figure here shows you A, B, and C in the plane. It doesn't show you the values. It just shows you the locations of points A, B, and C, okay? But keep in mind, if you calculate the value of the function at A, it should be the smallest. If you calculate the value of the function at B, it should be greater than this one. If you calculate the value of the function at C, it should be greater than the value of the function at this one, okay? And that's how you pick or how you label those 3 points. Okay, so you go for the point with the worst performance. What's the point of the worst performance in this case? C, because it has the highest value of the function, and our objective is to minimize, right? So this point C has the worst performance. And then you try to say, okay, since it has the worst performance, intuitively, I want to go away from that point to the opposite side. Opposite side. So how do you decide the opposite side? By connecting the A and B and then mirroring this across to the other side. Okay? So now I want to move from this location to another location, which is intuitively with respect to the other 2 points, as if I have jumped to the other side of the space. As if those 2 points are dividing the space here, and I want to jump all the way to the mirror location the other side, okay? And by doing this, you identify a point called E. Now you go and calculate the value of the function at E, okay? If you find that the value of the function at E is better than the value of the function at C, then this means that this move that you have done is a good move, right? But still, was this better than this and it's better than one of those, or better than both of them, or worse than both of them? Okay? So it depends. So for each one of those situations, you will do a different action. Okay? So let's see. If you jump to this point and you find that this point is better than one of those, let's say that E gives you a value of F better than B, okay, but worse than A, this means that your new search triangle is gonna be this guy, right? And the worst performer is gonna be point B. This is gonna be the next better performer, and this is gonna stay as the best performer at A, right? Okay. So now you have this new triangle. You repeat the same operation. You go to the worst performer, point B. You flip to the other side of the space. Now you flip around this line, right? And then you look at that point. You check if that point is giving you something better than one of the 2 points, right? Okay, or better than one of the points and smaller than the other one, or better than both of them, and then you move on again, okay? Similarly, if you flipped and you found this point being better than both of them, so better than A and B, right? Still, you can use this because it will become your best performer, right? And your A will become the second performer, and your B will become your worst performer. And again, you will do the flipping and you move on. One thing that you do whenever you find that this point is giving you a performance better than both of them is you say, okay, you become a little bit greedy. It seems that moving in this direction is doing something good, right? So you say, okay, I'll give it another try. I'll jump one more point, right? So I will jump, if I moved here, this distance, I'm gonna move from this point. Before doing anything, I'm gonna move further in the same direction. Because intuitively, when I moved in that direction, I got something better. So why not try to do another move, right? So you move another step and you calculate at the new point R. Now, if at the new point R, you get something better than E, this means that, oh, it's good. Maybe I can do one more, and so on, until at some point you see that this move is not doing you better. Then you stop. You don't jump further in that direction, and then you construct your new triangle and you start working on the new triangle, okay? Now what happens if when you do the flip to the other side and you find out actually that what you got here is worse than those two, right? Then what would you do in this situation? What you would do in this situation is you say, okay, let me try to do smaller moves rather than the big move to this side. So you go to this line that connects C to the new point E, right? And you divide it into 3 pieces. Okay, so this is gonna be 1 quarter of a jump, 2nd quarter, 3rd quarter, 4th quarter. Okay? And then you define point S1 and S2. For each one of those, S1 and S2, you do the same thing. Evaluate the function at S1, evaluate the function at S2. If any one of them gives you something better than the other 2 points, right, or better than the point C, then you move to it. What if both of them gives you something better? You choose the one that gives you the best among the 2 points, okay? What if they both fail to give you something better than the point C? In that case, you do something very interesting. You shrink the search space. So you go, remember originally we were dealing with A, B, and C, right? Now we say, okay, when we have been trying to do the A, B, and C, the search space, when I tried to look in the flip direction, all the trials here did not work. So what should I do? I will just move this line down a little bit. So I will move closer to the best performer, point A, by reducing the search space. So I will move point C to become C1, which is halfway between C and A. And also I will move point B to become M, which is halfway between B and A. And then my new search space is gonna be this small triangle. Evaluate the values of the function at C1, M, and A, and then start all over again in this smaller space, okay? This is called the Nelder-Mead method. There is proof that this method will actually converge to the optimal point, and you stop the search when those 3 points that you pick are very close to each other. So when they become almost identical to each other, it means that you have zoomed into almost a single point. And that's the point of your minimum value, okay? I have a nice demo that shows how this moves in actual space. Let me try to show it to you. Any questions? The equations here just explains when you are doing like the mirroring across, it's just basic geometry. So what is the actual distance that you move to the other way and so on. So these equations are simple. You can easily map them into the figure that you see here. Okay. Any questions about this method? No? Okay. Now what if you have more, now imagine that those points A, B, C are in two-dimensional space, right? So they have X and Y. And then there's a value of the function at each one of them. What if I am dealing with more than two-dimensional space? What if my independent variables are more than two? It's not only X and Y, so it's not just f of X and Y, it's f of X, Y, Z, L, M, N, and so on, okay? What should I do? In this case, I go to each two-dimensional space and I perform the same operation in an iterative way until eventually between every two variables, I will get a point, and then the collection of those x1, y1, and x2, y2, x3, y3, and so on will give me the final coordinate, which will have the best value of the function, the minimum value of the function, okay? So that's what's described in this is the code for the two-dimensional case, and then this is how you can iteratively call that two-dimensional code to do more than 2 dimensions. If you are dealing with more than 2 dimensions in terms of your search space, okay? I will just try to show you that animation. Okay, so there's also one of the most famous, this is actually the most famous approach in terms of solving multi-dimensional optimization problems. It's called the steepest descent. It means that you are coming from certain values of the function and you are trying to reach the point where you have the minimum value. So we are talking here about, by the way, for this one and the previous one, we are talking about functions with single minimum. So they are convex functions, okay? So if you can imagine, it's as if you are going down into the bottom of a valley, right? So you are descending down, right? So while doing this, the approach here is going to try to figure out the direction that will give you the most move downward, right? So imagine that if you have a valley like this, right? Now, let's imagine that this is like multi-dimensional, so I can explain it a little bit. I don't know if I can do a multi-dimensional thing or not. Let's see. Okay. Now, you have 2 ways, for example, of going down. You can decide to go down this way, moving in this direction, which means that you are not really, yes, you are getting to a smaller value, but you are not moving in the direction that gets you quicker to the smaller values, right? Or if your system is smart, it's gonna try to move in this direction. Right, so that it's taking the steepest, so imagine that this is a point like a surface going down. If you go this way, you are going fastest way to the minimum value or the value, right? If you go this way, you are going down very slowly. You are approaching down, but you are approaching down very slowly, right? So that's called the steepest descent. And the idea is very simple. You know what's the gradient? What's the gradient of a function? If you have a function of x1, x2, x3, for example, and you want to get the gradient of that, how do you calculate that? So let's say I have a function f of 3 variables. F of x1, x2, and x3. And I want to calculate the grad of f is equal to what? How do you get that? Differentiation. أيوة. Yeah. So the gradient, first of all, is a vector or a scalar quantity? Vector quantity. Right? And it is represented as you take the derivative of the function with respect to x1, right? And then this is as a vector is in the direction of x1 hat, right? And then plus the derivative of the function with respect to x2, and this is in the direction of x2 hat. So if you have, for example, this is axis x1, this is axis x2, and this is axis x3, so you take the derivative as a value of the function with respect to x1, and then this value is multiplied by a unit vector in the direction of x1, and then the derivative with respect to x2, and it is multiplied by a unit vector in the direction of x2, and then the derivative with x3 multiplied by a unit vector in the direction of x3. The vector sum of those three will give you what we call the gradient. The magnitude is going to be the magnitude of the gradient, and the direction is going to be the direction of steepest descent. So the gradient, mathematically, you can show that it points in the direction of maximum decrease. Okay? So plus partial f, partial x2, x3, and in the direction of x3. Okay? So that's the gradient in 3 dimensions. Of course, if you have 10 dimensions, you continue with this, with all x4 hat, x5 hat, up to x10 hat, and so on. Okay? So the important thing, not the magnitude, the important thing is that the direction of this vector, if you plot this vector in 3-dimensional space, is going to point in the direction of the steepest descent. It will point in the direction where you will have the maximum decrease if you move in that direction. But remember that this is calculated at every single point, right? So now if I calculate this at this point, right, at certain point, let's say I calculate this gradient at this point in space. And now I find out that it points in this direction. How much should I move in this direction?
Twice.
Why twice? Why not half? هو خلي بالك المفروض with every single step move from one point to the other, there is a chance that the direction is going to change. صح؟ لأنه now I'm going to evaluate the derivative at a new point, which means that it might have a slightly different direction. مظبوط? So you choose, in this case, you choose a step. So I will start at this point, I calculate the direction of the gradient. Okay? Now, this part of the equation is the gradient divided by its magnitude. Right? So it becomes unit vector in the direction of the gradient. It has no magnitude, it has unity. Now my question is, how much a magnitude should I move? Right? Now, in order to figure out the magnitude, you solve another optimization problem, which says that I want to pick the magnitude of that move in that direction, right? That gives me the minimum new value. So I will try with a very short, I know the direction, but I just need to try with different lengths until I find the one that will give me the minimum value. Now, rather than solving this by trial and error, this becomes a single-dimensional optimization problem by itself, right? So you can solve this by any numeric techniques of the ones that we mentioned before. To figure out how long is your step. So now you know the direction that you need to move in. What remains is how long I need to move in that direction, right? I choose the length that gives me the minimum value because I'm seeking the minimum. So if I choose one length that gives me, let's say, the value of f that I'm looking for, the function that I'm trying to minimize, equals to 0.7. And then I choose another length and give me a value of 1. And choose another length and give me a value of 0.3. I have to pick the 0.31. Because the other ones ended up with higher values of the function that I want to minimize, right? So that's why you try to solve this optimization problem to figure out the best step that you need to move with, okay? And then your new point becomes the previous point, xk1, right? And added to it, or subtracted from it, the step. So this will tell you what's gonna be your new point, right? And then this xk becomes your new, you plug it into this equation after calculating the gradient and the new one, right? And then you plug it into this equation, figure out the new step, and so on, And then you keep moving in the gradient direction at every point, right? With the length that gives you the best new value. And so on until you reach a point where what will happen? ليه هيبقوا close لبعض؟ حد عارف ليه؟ الجريدينت هيحصل له ايه بعد شويه؟ becomes very small and you are almost reaching the actual minimum point, صح؟ لأنه now at that point when you try to take the gradient it will have a zero value almost. خلاص you reach the minimum. Okay? So yes, this is gonna be also figured out by so this graph that was I will show you an animation as well. The graph that was shown on the right side of the previous slide was just showing you the moves as you do from one step to the other. Okay, this is also the code for steepest descent. Okay, and by the way, MATLAB already has a function that does the steepest descent optimization. There is also another optimization technique called the Newton's approach, and another one called gradient descent, not steepest descent. Okay, all of these are variants of the steepest descent, but the most commonly used one is the steepest descent. Okay, in some cases, Newton's approach is more efficient than the steepest. It can just reach the minimum point very quickly, faster than the steepest descent, but only under certain conditions. Okay, so what happens if I have to do an optimization on a problem that actually has multimodal function? So my problem has many minima and many maxima. How can I optimize? The only methodology that you have that can work with certain reliability, cannot guarantee 100% that you'll get the optimal solution, are random approaches. And the two most common randomized approaches to doing optimization are the simulated annealing and genetic algorithm. Okay. The general idea of, I'm not going to describe the algorithm itself, it's very complicated. You can look up the description for the algorithm, but just the general concept for you to understand why it works and how it works. Okay. The word annealing is, I think, very famous to mechanical engineering, maybe also civil engineering to some extent. Electrical engineering, they never hear that word before, and also similar to computer guys. So annealing is the process of cooling a metal very slowly, and the objective of doing this is that you reach a crystalline formation of that metal that has the minimal energy level among the atoms within the crystal. Why this is desired? Because this is a stable condition. It becomes very hard to disconnect or deform the crystal if it reaches that minimal energy level. That's the most stable level. Now, imagine that this happens, we do it, right, in manufacturing process, despite the fact that the energies of the atoms, the way they look to us, they are randomized, right? Because they can be arranged with respect to each other in any way, right? So the representation of that energy follows a random distribution, which is given by the Boltzmann energy equation. The probability of the energy of any formation of atoms is equal to some exponential function. So at some point, the probability that I have this particular value or the value of the energy between this range and this range follows an exponential distribution. Okay? Now, despite this being the case, and if you notice here in this expression, if you are working with temperatures that are very high, what will happen to this exponential distribution? So if you are working with T, very high number, what happens to this value? Becomes almost zero, right? Which means that the exponential is going to be almost flat, right? Okay. Similarly, the opposite, if you work with very low temperatures, what will happen? Yeah, the exponential is going to be varying very quickly, which means that you will have a probability of being in low energy much higher than the probability of being at high energy, right? So under this behavior, you can actually capitalize on this distribution, okay, by representing the value that you want to optimize as being the energy. Okay, so you replace this energy inside the exponential distribution with whatever you want to optimize. So your objective is to optimize, for example, the cost of constructing this building. And the way the parameters that affects that cost are the height of the building, the number of workers who are going to work, the sizes and the distribution of the pillars of the building and whatever. I'm not a civil engineer, so I don't know exactly, but these are all parameters that are contributing. And when you try to plot the cost function, you find that it has many maxima and many minima, and you don't know exactly how to reach the global minima or the global maximum, right? Then you take that function and you replace it in place of the energy here, right? So now you are trying to generate the values of the cost using this random distribution. And then you play the game of working with temperature that changes from high to low slowly in this distribution, which is going to actually result in very similar behavior to what happens to the atoms. And interestingly, in a very high percentage of the situations, the atoms will reach the point of the actual global minima. Similarly, the value of your function with that randomized generation, one time after the other, one iteration after the other, is going to become closer and closer because you are simulating the situation of slowing down or dropping down the temperature slowly, right? In this distribution. And every time you generate a new random value, and then you drop the temperature slowly, generate a new random value, and so on. One step after the other, you will be approaching in a randomized way the actual global minima of the energy, which is the actual global minima of your cost function, right? Again, you have to keep in mind that this is a random generator, right? So sometimes you will do the whole process and you will reach nothing, right? Just you will end up with, rather than minimizing your cost function, you'll end up with some random final cost function value, right? That's why we say for those approaches, almost, most of the time, almost guaranteed to reach a global minimum, but not 100% guaranteed. You can do a couple of trials, for example, not couple, I mean a good number of trials, and see between one and the other, does your final value change a lot, or you end up with the same value, then this will give you some confidence that you have actually succeeded in doing this operation, okay? That's how the simulated annealing works. I will also show you some animation of that one. And there is also another randomized approach, which both of them, by the way, are borrowed from nature, subhanAllah, okay? So the other approach is using the genetic behavior. So you remember that there is a general rule that says that genes in general, in their behavior, they always behave in such a way that they maintain the ones with desired properties, and the ones that are with undesired properties, they end up dying or disseminated as genes. They just disappear. Okay? That's called the survival of the fittest, which is taken sometimes to the extreme of evolution and all these things, right? So what you do in genetic behavior, you do exactly similar to the behavior of genes. So you have your function. You do a random change. That's called the mutation of the gene, right? What happens in a gene is one of the atoms inside the gene changes place, gets affected by some radiation or whatever, so it changes place. And then it changes the property of the gene, right? Then the body, by the creator, Allah subhanahu wa ta'ala, is built such that when this happens in a gene, if the person is normal, there are no big issues with the health or big issues with the genetics of that person, the body has some control system that goes and checks the genes versus each other and versus certain references. And if it finds that this new gene has certain properties that are weaker, they are evaluated in a certain way, then what's desired or what's existing, it just kills that gene. And if it finds that after this mutation, the gene has a desired property, for example, the gene is more resistant to, the new gene is more resistant to some types of virus, which happens when your immune system gets developed over the generations, right? Okay. So what it does is it produces more of that gene, so that it becomes the more dominant in the system. Okay. So that's the mutation. Mutation happens anyways, whether it happens actually intentionally from the body itself during the normal process. It's a random variation to see if there is something better than where I am right now, okay? Or it happens because of external factors. So mutation happens, the control system in the body does the comparison, and then it decides that the ones that has undesired, which means that it has a cost function, for example, higher than the existing ones, and I want to minimize. So those ones are discarded, they are dismantled, they are killed. And then only the ones that are better survives. And then they get reproduced. This is just the equation of the reproduction, right? And then you repeat the operation again. Similarly, you can do this with your function. So you mute the variables of the function. You change them randomly. You calculate the new value of the function. You compare that with what you have right now. You find that it is not the fittest. You kill it, and then you reproduce the better ones. You find that it is better, then you multiply and reproduce that more and more, so that you become closer and closer to your optimal point that you are looking for, okay? So these are two algorithms that when you are stuck in your research or in your work and you want to actually optimize a multimodal function, which happens a lot actually, okay, then you can opt for those ones. Again, they are not 100% guaranteed, but with very high probability, they will give you the global optimal that you are looking for. Now, each one of those has lots of parameters. Like, for example, the alpha in the upper one, which is represented by the K and T, the Boltzmann variable and the temperature. How fast you vary the temperature, what's the step from one iteration to the next, right, in terms of varying the temperature and so on. These parameters, typically, you either have some intuition from the problem itself, or you have to do some trial and error with those parameters until you reach a good performance in your optimization algorithm. Similarly, the same thing for the genetic algorithm. It has also many parameters that you have to control, okay? Okay, one last thing that I'm going to discuss, and then we are finished with this lecture. I know that you might get bored and sleepy or something, so. All the previous situations we have been talking about, you have a function of multiple variables or a single variable, right? And you are trying to get the minimum or the maximum of that function. In real life, especially when you are working in design problems, right? In engineering problems in general, you don't only have a function that you want to optimize, you want to optimize this function under certain constraints that are forced on you. For example, you want to optimize the cost, but probably the optimal cost is going to happen if you build this building in 5 years. But then the owner is asking you that you cannot exceed 3 years of time, and you have to establish, so that's a constraint, right? That's one variable that you cannot exceed a certain value, right? Similarly, the owner might tell you under the condition that the number of workers in my company cannot exceed 30 workers, right? So now you have to optimize your situation without violating the constraints, okay? In general, when you deal with constrained optimization, the general approach, and that's an analytic approach, which is also applied when you are dealing with numerical approaches, you convert the constrained problem into an unconstrained problem. And that's allowed, or that's enabled by what's called the Lagrange multiplier. I think probably all of you knows the Lagrange multiplier approach, right? So the approach says that if you have a certain function that you want to optimize, and you have certain equality constraints, so certain functions, right, that cannot deviate from a certain value. So these are equality. So you have h1 equal to 0, h2 equal to 0, h3, and so on. These are sets of functions with equalities. These are equality constraints. Then solving this problem is exactly equivalent to solving this unconstrained problem which is formulated by taking the function that you want to minimize and adding to it all the constraints to the function multiplied by something called the Lagrange multiplier, right? And then you try to minimize this whole thing, and if you find the minima of this, it's going to be exactly similar to the minima of this one. Okay? So if you figure out the values of x1, x2, x3, that gives you the minimum value of this Lagrange multiplier or Lagrange formulated problem, those x1, x2, x3, and so on are going to give you the minimum value for f of x by itself. Okay? And there is a mathematical proof why this works. Okay? The issue is, in many cases, your constraints are not really equality. So it doesn't say that you have to finish this building in exactly 3 years. It just says you should not exceed 3 years. So if you do less than 3 years, everyone's happy, right? Similarly, it cannot say that you have to build this building using only 12 workers. No, it says I don't want the total number of workers to exceed 15 or 30, right? Then if you work with less than that, it's fine, okay? Now, solving those constraint problems that have inequalities in them cannot just directly be applied by the Lagrange multiplier, because the Lagrange multiplier works with equality. The trick that you play in that case is you convert. So remember, when you did the Lagrange multiplier, you introduced to the problem new set of variables, right? Those lambdas, right? Similarly, when you have inequality constraints, you introduce new variables to the problem. They are called slack variables, right? And then it becomes, when you say that g of x is smaller than 0, smaller than or equal to 0, you can say, okay, it must be, there must be some value which is added to g of x that makes it equal to 0, right? So you say, okay, I can convert this into the equality that g of x plus some slack variable is equal to 0. And of course, in this case, this variable has to be if g of x is positive, can this variable be negative?
If it is no.
Because the condition here says less than or equal, right? So if this is a negative, definitely it's not going to take g to be equal to 0, because g was originally less than or equal to 0, right? So why am I pointing this? Because when you introduce those slack variables and you start solving the problem, of course it becomes again formulated as the Lagrange, but now the equality constraints will include inside them those slack variables, right? And then you optimize the problem, you find the optimal solution, x1, x2, x3, and so on. But while doing that, you will also have to find the value of those slack variables, right? And there are certain conditions on those slack variables. If they don't satisfy, you know that what you found using the Lagrange multiplier is not the optimal solution. So in this case, the Lagrange multiplier is not guaranteed to give you the optimal solution, except under certain conditions on the slack variables. And I just gave you one quick reason why, right? If you find out that with the Lagrange solution and everything, you end up with, for this particular less than or equal to constraint, and you know that this is a positive function, and then you end up in the solution that y is a negative value, then this means that what you found is slightly violating this condition. So it's not really the optimal solution, okay? So that's why I just wanted to point out this. But again, it's a very famous trick to actually solve constrained optimization problems. Last but not least, these are some very important functions that you will use from MATLAB, particularly the last two. Okay? So there is one called fmin unconstrained. This solves problems that does not have constraints. And then the next one is fmin con. Minimize a function under certain constraints. And for each one of them, there's a format how you pass the constraints, how you pass the function itself. And then these are using multiple techniques, and they use multiple variations of different techniques. And even for non-convex functions, they work in most of the cases, except when the function gives you an error that it cannot converge. Other than that, they have really very nice algorithms that enables you to solve many. They are many of the optimizations. So they are very nice when you are doing your research. Of course, you cannot just claim that you did some optimization by just putting the problem into fmin con. especially if you are doing a PhD. However, they are good checkpoints. So you do whatever you are doing analytically and you try to solve the problem with all other numerical techniques and so on, and then eventually you compare your result with FMINCON, and that gives you some confidence that the results that you have reached are good enough. Okay? So these functions. Also, if you are working with problems that you know that they are convex, there is a very nice tool set designed for MATLAB, and it exists on the webpage of this Stanford faculty. This guy is like the father of optimization, specifically convex optimization in our generation. Okay, it's called Stephen Boyd. Okay, so Stephen Boyd has a very nice webpage with this CVX tool. It works on Python, it works on MATLAB, so he has different versions of the same tool. Has lots of convex optimization methods implemented in that library. Okay, so you can also capitalize on that if you want to solve a problem that you know that it is convex. Okay. Of course, the domain of optimization is much wider than this. There are problems that look initially that they look like they are non-convex, but then you can map them into other problems, and they become very equivalent problems, and they become convex, and then you solve that. Then the solution that you find to that is applied to your original problem. There are many things that you can do in optimization, but I just wanted to touch upon the topic because it's quite common in any research that you do. Okay. Any questions, Shabab?